Hello everyone, welcome back to my YouTube channel. Today's topic is adjacency list in graph data structures. This is very important concept in algorithms such as DFS, BFS and shortest path algorithms. By the end of this video, you will clearly understand what an adjacency list, how it works and when to use it. So let's begin our video. Firstly, let's take some idea about graph. A graph is a collection of nodes, also called vertices. These vertices are connected using edges. Graphs are used to represent relationships such as cities connected by roads, users connected on social media, and computers in network. So, every graph has two main parts. The first part is vertices, also known as nodes, and the second part is edges. So the vertices are connected using these edges. Without these edges, vertices are just isolated points. The structure of graph depends entirely on how vertices are connected. Next, we'll talk about two main types of graph. The first type is undirected graphs. In this graph, the connection works both ways. So if A is connected to B, then B is also connected to A. Second, we will talk about directed graph. So in this graph, edges have directions. A to B does not mean B to A. So this difference is very important when building adjacency list. Now the question is, how do we store these graphs in memory? There are two common methods to store. The first one is adjacency matrix and the second one is adjacency list. In this video, I am going to focus on adjacency list because it is more efficient and widely used. So, what is an adjacency list? An adjacency list is a way to represent a graph where each vertex stores a list of its connected vertices. In simple words, each node keeps a list of its neighbors. For example, in this graph, vertex A is connected to vertex E and D. So, A's list contains E and D. In memory, we typically use arrays or maps for vertices as well as lists for neighbors. Now I am going to show you how we can use adjacency list on directed graph. Now let's look at this concrete example using directed graph. In a directed graph, the direction of edge matters. We only record outgoing edges for each vertex. Look at this diagram. We have four vertices A, B, C and D. First I am looking to vertex A. A has two outgoing edges as you can see, one to B and one to C. So A's adjacency list contains B and C. Next I am going to vertex B. B has outgoing edges to vertex C and vertex D. So B's list contains C and D. Next I am moving to vertex C. C has only one outgoing edge which point to D. So C's list contains only D. Finally, vertex D. D has no outgoing edges, so its adjacency list is empty. This clearly shows how adjacency list stores only meaningful directed connections. Next, I am going to show you how we can use adjacency list on undirected graphs. Now, let's look at this example using undirected graph. In an undirected graph, connection works both ways. If A is connected to B, then B is always connected to A. As a step 1, I am going to vertex A. So A is connected to B and C. So we store B and C in A's adjacency list. Next I am going to vertex B. B is connected to A, C and D. Because the graph is undirected, all three connections matter. So B's list becomes A, C and D. Next I am moving to vertex C. C is connected to A, B and D. We add all three C's adjacency list. Finally, I am moving to vertex D. D is connected to vertex B and C. So D's list contains B and C. Now the adjacency list is complete. Each edge appears twice, once for each direction. This is the key feature of undirected graphs. Now let's clearly compare adjacency list and adjacency matrix. First, we look into representation. In an adjacency list, each vertex stores a list of its adjacent or connected vertices. In contrast, an adjacency matrix uses a 2D array where matrix I and j tells us whether there is an edge between vertex I and vertex j. Next, we look into memory usage. Adjacency lists are very memory efficient, especially for sparse graphs where only a few connections exist. Adjacency matrices consume much more memory because they store information for very possible pair of vertices. Now, space complexity. Adjacency list require O V plus E space where V is the number of vertices and E is the number of edges. And adjacency matrices require O V square space since we must locate a full matrix regardless of how many edges actually exist. Let's talk about edge lookup. With an adjacency matrix, checking whether an edge exists is extremely fast, just one lookup or one time. With an adjacency list, we need to search through a vertex neighbors, which takes degree of vertex time. Next, we look into graph type base 4, and adjacency lists are best suited for sparse graphs where edges are much fewer than vertices. Adjacency matrices are more suitable for dense graphs where most vertices are connected. Finally, we are moving on implementation and real-world usage. And adjacency matrices are very simple to implement using 2D arrays. And adjacency lists are slightly more complex because they use a list or linked structures, but they are more flexible. Real-world usage. And adjacency lists are widely used in real-world systems like social network and maps where graphs are large and sparse. Adjacency matrices are usually used for small or dense graphs or in cases where fast edge lookup is required. So overall, adjacency lists are more memory efficient and practical while adjacency matrices are simpler but memory heavy. To sum up my YouTube video, adjacency list and adjacency matrices are two different ways to represent graph. But adjacency lists are more efficient for most real-world problems. By storing the actual connection, adjacency list saves memory and work best for large or sparse graphs. This is why they are widely used in practical applications and forms the foundation for graph algorithms such as BFS and DFS. So, thank you for watching. I'll see you in the next video.